In this lecture, we are going to discuss reinforcement learning from a more technical standpoint, and this will allow us to define most of the terminology involved in reinforcement learning problems. I'm a big believer in learning by example, so in this lecture, it's not going to be so much about abstract and technical definitions as it is about providing examples of everything. Let's start with the main objects in a reinforcement learning problem, the agent and the environment. The best example of this is yourself. You are an agent, and the world is your environment. Maybe your long-term goal is to ace your math exam. And so, just like an autonomous vehicle driving to a destination, you must observe your environment and make the correct decisions every day in order to achieve your goal. That means studying, going to class, taking notes, doing your homework, asking questions when you are confused, and so on. So that's one basic example. Here's another example that's closer to what we might actually use reinforcement learning for. Suppose you're writing a program that plays tic-tac-toe. What's the agent and what's the environment? In this case, the environment is composed of the computer program that implements this tic-tac-toe game. Of course, this computer program may also involve some form of AI that will be the other player in the game, but for all intents and purposes, just pretend it's a bunch of if statements and predefined rules. So it's not intelligence per se, it's just a computer program written by someone else, just part of the greater tic-tac-toe program. You can imagine that this tic-tac-toe program will have an API that will allow you to interact with it programmatically. So for example, there might be a function to start a new game. There might be a function to place your X or your O at some location on the board. There might be a function to read the state of the board so you can see where all the X's and O's have been placed so far. There might be a function to check whether the game is over, and if so, who won the game, the computer or your agent. So that's the environment. Your agent, on the other hand, will be another computer program that interfaces with the tic-tac-toe game. Your agent may use an algorithm, such as one from reinforcement learning, in order to learn how to play tic-tac-toe from experience. It makes use of the API to interface with the environment. So here we have a program that plays the game. Part of this code is where the agent reads the state of the game board and chooses the most intelligent action. That's our AI, represented by our agent. Here's another popular example, video games. This is a famous classic Atari game known as Breakout. By the way, if you don't know how this game works, there are many places where you can play this game online for free. So if you've never played this game before, please go and give it a try. In this game, the environment is obviously the game itself. The goal is to clear all the blocks, and your job is to move the paddle in such a way that the ball destroys the blocks but never falls to the ground. The agent would be your computer program, which can read information from the game, like what the screen currently looks like. So it can figure out where the blocks are, where the paddle is, where the ball is going, and so forth. Its job is to control where the paddle goes. So basically, you can move left, right, or do nothing. Next, let's continue defining more terms. So far, you know about the agent and the environment. The next term I want to define is episode. What happens when I play a game of tic-tac-toe or breakout? Well, some sequence of events will occur, and then at the end, I will win or lose. With my math exam example, you will take your math exam, and then you'll get your grade. Now we know that with learning algorithms, the way that they learn is with data. So if you're training a dog versus cat classifier, you'll need lots of labeled images of dogs and cats. Similarly, with tic-tac-toe or breakout, once the game is over, I can opt to play again. This is the method through which I will gain experience, or to be more technical, data. You might call these games or rounds or matches, but in reinforcement learning, the official term is episode. So when you're training an agent to play tic-tac-toe, you're going to play multiple episodes, and at the end of each episode, your agent will have won or lost. Hopefully, by the end of the training process, or in other words, after many episodes, your agent will be winning more than losing. Of course, not all reinforcement learning environments are episodic. To say an environment is episodic means that they end at some point and you can start again with a new, fresh episode. Furthermore, there is no relationship between one episode and the next. So the fact that I lost the previous tic-tac-toe episode will have no effect on the environment in the next episode. However, there are examples of non-episodic environments. Take, for example, the stock market. For all intents and purposes, this can go on forever. There's no real notion of the end. Well, if you lose all your money, then technically there is nothing more you can do. But it's not the same as losing a game of tic-tac-toe and starting again. You can't go back in time and restart the stock market. Another example is an online advertising system. Your agent's job will be to choose the right advertisements to show to users at any given moment in order to maximize your company's revenue. It should do this continuously. There's no concept of an end to an online advertising service. Alright, so those are some examples of some non-episodic environments. We can refer to such environments as having infinite horizons. Alright, so to recap the terms we've discussed so far, now we have agent, environment, and episode. The next few terms I would like to think about are the state, action, and reward. These items help us describe what goes on when the agent and environment interact. Let's again use our tic-tac-toe example. In this scenario, the state would be the configuration of the board. So for each position on the board, I want to know, is there an X there, is there an O there, or is it empty? This information is all that I need in order for my agent to make an intelligent decision about what move to play next. Speaking of which, the moves that the agent makes are what we refer to as the action. So in tic-tac-toe, to take an action would mean placing a new X or an O somewhere on the board. Finally, the reward is just a number that you can receive at any moment as you play an episode of the game. By the way, keep in mind when I say the word game, I don't necessarily mean a board game like tic-tac-toe or a video game like Breakout. When I say game, I mean it in more of a generic sense. In any case, perhaps the reward you get in tic-tac-toe may be +1 for winning, -1 for losing, and 0 for draw. Although this is just an example. In general, you can always assign rewards yourself in order to improve the training of your reinforcement learning agent. Here's another example of states, actions, and rewards. Think of a maze. In this maze, the state is your position in the maze. Your actions may consist of the various directions you can go. For example, up, down, left, or right. The reward is tricky. Remember, I said it's up to you to think of a good reward to assign to your agent to encourage it to learn how to solve the environment. You might say +1 for solving the maze and 0 otherwise. But ask yourself, is this a good strategy? Imagine you throw your agent into this maze and it has to learn what to do. Imagine your agent has played this game 10,000 times and has never solved the maze. We can pretend the environment is episodic so that after taking 100 steps, you reach a terminal state and the game is over. What happens if we get 0 reward each time? Well, in that case, the agent learns that it does not matter at all what it does because doing anything always leads to the same reward, 0. In this case, the agent has no incentive to solve the maze. Your agent will never prioritize one action over another because it knows that no matter what it does, it always gets 0 reward. In this case, all actions are equal. Perhaps a better reward structure would be to assign -1 reward at every state. In this case, you can maximize your reward by solving the maze as fast as possible. Doing any extraneous actions will lead to a more negative reward. Not solving the maze will lead to the most negative reward. So in this case, assigning a negative reward upon reaching any state will allow your agent to solve the environment. Now you have to keep in mind, this is not English class, so you have to remove any bias you may have about what connotations are associated with the term reward. You might think of reward as a good thing, like a prize. For example, if you're a dog and you have just successfully completed a trick, your owner may give you a treat as a reward. But in reinforcement learning, this is not what we mean by reward. The only constraint is that the reward is a real number. It can be positive, negative, or zero. You will also receive this number at every step in the environment, not just when you reach some goal or definitively fail to achieve it. The agent, as you will learn later in this section, will try to maximize its reward over each episode. For example, you may get a reward of -100. This is better than a reward of -1,000,000. Maybe -100 reward corresponds to successfully solving the environment. But in the end, it's just a number. Don't associate -100 with negative connotation and +100 with positive connotation. So just remember this, the reward is not a prize, the reward is a number which is to be maximized. You can think of it as kind of the opposite of a loss function. Whereas we want to minimize the loss in a supervised or unsupervised learning problem, in reinforcement learning, we want to maximize reward. Since I love examples, here's one more. Imagine again the game Breakout. In this case, we actually have several options for the state. For example, we may have perfect information about the game. We could be told the exact positions of all the blocks. We could be told the position and velocity of the ball. We could be told the location of our paddle. And we could be told our current score and the number of lives we have left. Although I think you'll find that most reinforcement learning applications do not make use of such information. Another way you can read the information about the state of the environment in Breakout is to look at the game's RAM. In other words, look at the values it has stored in memory. In contrast to the above, this actually is one method used in modern reinforcement learning applications. It's a proxy to the above perfectly defined state. You can imagine that it should be quite possible to derive the locations of the blocks and the position and velocity of the ball and so forth from the values stored in RAM. Although I think the most common way to represent the state in contemporary reinforcement learning is to use screenshots from the game. In this way, our reinforcement learning agent is learning to interpret images of the video game just as we do as humans. I think this is the most meaningful because it's the closest match to how you and I play video games. We look at the screen. You can imagine that models like convolutional neural networks would be useful here. One complication that can arise from only looking at images of the screen is that you don't really have information about movement. An image is only a frozen picture of the game at a single point in time. Looking at this image, how can I tell which direction the ball is moving? And so this allows us to consider an important point. The state need not be what I observe in the environment. It can also be information derived from both current and past observations. So one way of dealing with the problem of frozen pictures is to simply include past frames as well. In the famous DQN paper, they use the most recent 4 consecutive frames of the game to represent a single state. To get back to our states, actions, and rewards, the rest of it is quite basic. The actions consist of the various moves you can do in the game. You can think of this in terms of pressing buttons on a joystick or a control pad. In Breakout, you can move the paddle left or right. For the reward, as an example, you might get +1 reward every time you destroy a block. As a final note in this lecture, I want to introduce you to the concept of state spaces and action spaces. This is important as we move down from high-level ideas and concepts to the actual math that will allow us to solve reinforcement learning problems. The particular math concept that we need to describe state spaces and action spaces is the set. The state space is the set of all possible states, and the action space is the set of all possible actions. We don't need to go further than this, we just need to know what it means. So as an example, consider the canonical example of a reinforcement learning problem, known as grid world. In grid world, the idea is you're going to start in the bottom left square, and your goal is to arrive at the top right square where the ruby is. If you make it there, you get a reward of +1. Below that, there is a losing state where if you arrive there, you get a reward of -1. And in the second row, second column, there is a wall, meaning that your agent cannot go to that square. So that's the basics of the game. To describe the state space, that's simply the set of all possible positions on the board. So you may want to pause this video and look closely at this list of coordinates to confirm that they correspond to positions on the board. The action space consists of the actions up, down, left, and right. Now, the reason we had to talk about grid world for a bit is because for our other examples, such as tic-tac-toe and breakout, the state space is much more complicated. The action spaces are pretty simple, since for tic-tac-toe, it consists of all the possible positions. You can draw an X or an O. And for breakout, it consists of moving left, right, or doing nothing. But for tic-tac-toe, the state space is quite large as there are many possible configurations of the board. As an exercise, I would strongly recommend trying to write a computer program that can enumerate all the possible configurations of a tic-tac-toe board. This should give you some intuition about why games like chess and Go are very difficult. You can imagine that if a 3x3 board with only 2 possible characters can have thousands of states, imagine how many states are involved in chess and Go. For breakout, the number of states is even larger. It's equal to the screen resolution multiplied by the number of possible colors per pixel, 2 to the power 24, or 2 to the power 8 to the power 3. But for all intents and purposes, we can consider images, just like time series, to be continuous valued. The only reason they appear to be discrete is because computers have finite precision, and so the values need to be quantized. When we have continuous values, this means that the number of possible values is actually infinite. In fact, it's possible for actions to be continuous also, so that the action space is also infinite. Since this lecture was quite long, let's summarize everything we learned. This lecture was all about defining some reinforcement learning terminology to help us in our discussion of reinforcement learning. First, we define the terms agent and environment. You can think of the environment as the world, or whatever computer game you are teaching your agent to win. You can think of your agent as your computer program, the one that does the learning. Next, we define the term episode. This is like one round or one match of a game. As you know, machine learning models learn through data, or in reinforcement learning parlance, experience. And so you can imagine that in order to sufficiently learn how to play a game, this is going to require multiple episodes. Next, we learn about states, actions, and rewards. Rewards are a number which can be any number, positive or negative. The job of a reinforcement learning agent is to maximize its reward. Actions are what an agent does in an environment. For example, playing a move in tic-tac-toe or going left or right in a video game. States are what we observe from the environment, but they can also be values derived from those observations, or even a sequence of past observations. To add a little more to this, we call the last state of an episode a terminal state. So when you reach a terminal state, that is the end of your episode. Lastly, we define the terms state space and action space. These are the set of all states and the set of all actions, respectively. Using these terms, we can now talk about reinforcement learning coherently and build a framework that allows us to solve reinforcement learning problems.